Well, so one of the videos they talk about in the textbook is a bicycle race versus a car versus an airplane. So what you expect is going to happen in this race. It's going to be a race along a jet run. What do you expect? How many of you vote for the airplane to win? How many vote for the motorbike? How many vote for the car? Okay. Well, let's watch the video and see what happens. Sorry, such low resolution. In the book, they show a four-door sedan, not a car. Okay, so probably what you expected to happened for probably most of you. What you expect is the motorbike is probably going to accelerate faster. That's why in these roadway chases, if you ever watch, you don't have 5 minutes spare every now and then, you watch a motorbike trying to run away from a police car, right? What happens is that the motorbike continually makes turns and stuff like that because they have much better acceleration than a typical car. But the car has much higher end velocity. So it's really hard to get a motorbike going over 200 miles per hour. In fact, a few years ago, a police helicopter taped a motorbike doing a quarter mile in 3.96 seconds. And this motorbiker was very famous. He was illegally doing this, but that's quite impressive in terms of a quarter mile, simply because motorbikes have a very difficult time getting up to high speeds. Whereas an airplane, you would expect to go very fast, but maybe not necessarily very fast at the beginning. So there's acceleration, there's terminal velocity, there's a lot of things that come into play in this one-dimensional motion. And what we're going to be talking about today is basically motion along a straight line. And we're not going to worry about two-dimensional motion yet. We'll get to that in a couple of class periods. But if you think about it, everything moves. And this is one of the beautiful things that Einstein pointed out in this theory of relativity, that Earth is moving through the solar system. The solar system is moving. We're moving relative to other galaxies. Things are just in constant motion. So we have to think about it, about everything being in motion. Now, what we're going to be studying is essentially what we consider to be particle motion. Now, what we mean by particle motion is that, for example, if I consider an object, a relatively large object, it's obviously not a particle, but if I consider every part of that object to be moving with the same speed, I can treat it like a particle. And what I mean by particle is just a point mass moving with a particular velocity. So we'll get to this in just, well, maybe I'll do this right now, just so we can take this off the screen. Okay, so what I have here is I have a series of black stripes and then clear stripes. And what this is going to do is this is going to fall through essentially a laser beam that tells it when it turns on and off. And what it does is it takes the time interval between each of these stripes. Now what we're hoping to show is that as this drops, because it's undergoing uniform acceleration, we will see that the velocity is linearly increasing with time. And from that, we can determine the acceleration of this object as it passes through this laser beam. So let's run this. Okay, so we have our data here. Now, if I look at this, okay. So what we found here is what we did is we just did a slope measurement, and what this showed is that we have 9.38. Now, actually, it's 9.8. But what it's doing here is on the left-hand side, along this axis, we are seeing the velocity, and on here, we're seeing the time. And what we're seeing is that as a function of time, this velocity, the velocity of that thing falling increased linear with time. And if we take that, we take the slope of that function, what we find out is the acceleration, or the change in the velocity as a function of time. So that's a nice little way of demonstrating what the acceleration due to gravity is. Okay. Any questions about that? All right. Okay. Do you like me using the big chalk or the smaller chalk better? Yes. Big? I would prefer big. Okay. Okay, so when we talk about motion in a straight line, what we're going to say is we have some axis here. We're just going to refer to it as the x-axis. And then we define an origin. What is an origin? It's just the place where we define to be 0. So if I define the origin to be here, and I move this way, and I consider this to be the positive x-axis, then I've moved whatever that distance is relative to the origin. If I move this side of that origin, then I've moved in a negative direction. Okay? So we're going to just call this the x-axis. And what we're going to do is look at displacement. So suppose I have position 1 and I have position 2. I'm interested in the displacement. Displacement we define as delta x. Okay? This is the delta is just a Greek symbol that means change in, okay? And x is just our position. And so what we define this is x2 minus x1. All right. So if delta x, okay, so delta x is the displacement. It's this. It's the change in the position. Now, if the displacement is positive, okay, so delta x is equal to x2 minus x1. If x2 is greater than x1, then delta x is positive. And if delta x is less than, delta x is less, if x2 is less than x1, then delta x is negative. Now this becomes important. because we need to keep signs, especially when we start talking about vectors, we need to keep track of whether it's positive or negative. When we talk about vectors, displacement is a vector when we start looking at multiple dimensions. And we need both its magnitude and direction. For these one-dimensional systems, the magnitude is simply the distance between x2 and x1, and the direction is denoted by either positive or negative. So in this particular case, x2 is greater than x1, so the displacement is positive. So I'm sure this is very familiar to most of you, but you need to keep track of these sorts of things. Now, displacement, it only depends on the end point and the initial point. It only depends on x2 and x1, which means that if an object goes, for example, from x1 past x2, goes, say, negative, and then goes to x2, all that matters is the difference between x1 and x2. That lengthy trip that it might have taken does not matter. Okay? So it only depends on the two endpoints, x2 and x1, and not on anything in between. Okay? So we would ignore, for example, if it does something like this, we would ignore that trajectory. Okay? All we're interested in is what happens between the two endpoints. All right. So how do we show position as a function of time? So what we're going to show is we have time, and we want to show that position is dependent on time. And so what we're going to do is we draw axes that look like this. Okay? We have the position, and we have time, and we want to show how position is a function of time. Okay? Now, with projectile motion, so for example, one of the reasons I wanted to make this pneumatic device is simply because it's a very good way of showing constant force. It's going to be very useful when we talk about pressure and things along that line. But basically, if you look at projectile motion, what happens in this particular system is it undergoes a quadratic type of position, and then what happens, so it's moving along, and it's getting its position as a function of time is getting further and further away, but it's also growing. Its rate at which it's getting further away from the origin is growing. And when it gets down to the end of the region where it's accelerated, then it just undergoes straight line motion, which is something like this. Okay? So this would be the point when it, for example, leaves the end of the pipe in this particular, just PVC pipe. So it undergoes this quadratic behavior, and then it just has a linear behavior, which means that once it leaves the pipe, then it's just traveling at constant velocity because there's no more force acting on it. But is that really true? Once it leaves the pipe, then what's happening? What's the dominant force acting on it? Okay, so it has gravity acting perpendicular to it, but it also has wind resistance. Right? And that wind resistance is a function of the velocity that it's traveling. Okay, so this is the projectile motion. So it looks something like this. So I just did some quick calculations, and I can adjust it to however I want it, but the important part is that this is, so for example, after say about 0.05 seconds, it's going to come out, and then, and what I did is I said, well, I'm going to make this a meter long, and so it comes out at one meter long pipe, and it takes about 0.05 seconds, and then it goes 2 more meters in the next 0.05 seconds. it then travels at that constant velocity and goes 2 more meters in the next 20th of a second. Okay, so that's roughly about the projectile motion that we would expect to see for this type of system. Now we'll get into some more numbers as we go on, but I just want to bring those up at this point. Okay, now, so if you're watching a race that's going on a circular track, right, such as NASCAR, what is the average velocity of the NASCAR race? 0. Why is it 0?
Because you're going around in a circle. So the velocity is always key.
Well, if you think about what's the total displacement between the time they start and when they end, the displacement is 0, right? Even though they may have done 500 laps, for example, or gone 500 miles. The average speed, though, on that track, well, it depends on the type of race, right? But the average speed may be 225 miles an hour, right? But the average velocity is 0 if you take from the beginning to the end of the race. Okay, so there's some important things to remember. So speed is simply what we call a scalar, which tells you how much distance per unit time it's undergoing, whereas velocity says how much displacement as a function of time is occurring. So we write so this just means speed average. The average speed is equal to the total distance divided by time. So in this particular instance, what we said is the displacement is x2 minus x1, but the distance that it traveled, we would keep in mind that it went along this complete trajectory. So the speed in this particular case would be much higher than the velocity. Okay, so they give an example in the text, which they call the beat-up truck. What they should call it is the empty gasoline tank truck. So what happens is this truck is traveling at 8.4 kilometers. Traveled 8.4 kilometers at 70 kilometers per hour. Okay? Then it ran out of gasoline, and the owner had to walk 2 kilometers in 0.5 hours. Okay? So what is the total displacement? So what we're going to assume is that it travels for 8.4 kilometers, runs out of gasoline, and then the owner walks 2 more kilometers. So what is the total displacement? 10.4, okay? Okay, so we moved a total displacement of 10.4 kilometers. Okay, now what is the driving time interval? How can we find the driving time interval? Yeah. Okay, so good. So basically, we know how far it went, and we know the speed at which it was going. And so by that, we can find out the total time. So if we just look at this equation, I was going to say we haven't actually written it down yet. But if I look at this, for example, we're only doing one dimension. So if I take the total distance, right, 8.4 kilometers, and I know what the speed was over that distance, then I just simply take S average, put it in the denominator, T, put it up here. So I take the total distance, which is 8.4 kilometers, divided by 70 kilometers. Okay? So T is 8.4 kilometers divided by 70 kilometers per hour. Now, one of the nice things about keeping track of units is that you can see kilometers cancel. I have 1 over hour in the denominator, which is the same as putting it in the numerator. And so you see that I have something, once again, as a function of time. Okay. And this gives us 0.12 hours. So he was traveling 0.12 hours in the truck when it ran out of gasoline. All right. So if I look at the total time interval is then the time that was spent in the truck and the time that was spent walking. Right? So the total time is okay, 0.62 hours. Okay. And now, what is the average velocity? Okay. So average velocity, which I should have written earlier, the average is just going to be the change in x, the displacement, divided by the change in time. Okay? In this particular case, the change in time goes from the time final, which is 0.62 hours, back to when we started driving the truck, which was what we're going to call time 0. Okay? So delta x is 10.4 kilometers divided by 0.62 hours. And I think that's about 17 kilometers per hour. So, yes?
First question about it is, they didn't say that the drivers walk in the same direction as the truck, so how will you assume that?
So, yeah, so that's a good point. So what you're saying is, we're assuming 1D motion. What we say is that they started driving out here, we got to a point, and then the gas station is right here. But in the book, I can't remember exactly what it says, but this is what is meant. Okay, good question. Any other questions? And this is a good point, because if he had actually passed a gas station and went back, right, then x2 minus x1 would actually be smaller, and his average velocity would be smaller than 17 and would actually decrease quite a bit as he walked back. Okay? So if he goes 8.4 and then goes minus 2, then that leaves us with something else. Okay. calculus is an absolutely beautiful subject. I know you may not think it is, and many of you probably just memorized a lot of the equations in it, but there's so many remarkable things, and a lot of it was basically physicists who couldn't figure out how to describe nature without actually bringing in these sorts of principles. And so calculus was based on that. Newton and Leibniz just did an enormous number of beautiful things. And once you begin to understand calculus, it really opens up the world of physics. And so much of physics is based on what we can learn from calculus. So I want to talk just a little bit about calculus for a bit. Okay? So many of you are probably familiar with seeing functions that look like this. And you have, for example, y on one axis and x on another axis. You say y is a function of x. Or you say f of x and then x. Okay? You have some independent variable and some dependent variable. Okay, now what is a derivative? Well, if you think about this for a moment, suppose I have something that's undergoing motion that looks like this. In other words, with each passing moment, its displacement, its rate at which displacement is occurring is getting faster and faster. Okay? And if it was quadratic, that would be uniform acceleration, okay? Constant acceleration. So we then ask, so suppose I have at some time, I'm just going to call it t1, I say I'm at some position x1, okay? And then I want to go to some time at t2, and then I'm going to say I have some position x2. Now, I ask, what is the average velocity during that time interval? Well, what I would do is I would draw a straight line, because delta x, right, velocity average, is equal to delta x over delta t. And delta x in this case is x2 minus x1 over t2 minus t1. So I just take this change in position here, and I take this change in time here. Okay? Now in this particular case, x2 is larger than x1, and t2 is larger than t1. And so, well, time is always progressing. So if I take this, that means I'm undergoing an average, positive average velocity. If I just look at this slope. Now, is the speed, the average speed along here, the same as the speed at this point right here? I'm going to vote yes. I'm going to vote no. Okay. Would it be greater here or less than the speed at this, for the average interval? So this is going to be less than, right? However, up here, right, the speed is going to be greater. Now, let's just think about something undergoing uniform acceleration. For example, a projectile in just this pipe I'm talking about, where you have a constant force. At time 0, what's its velocity? 0. I have at time 0, that's when I trigger air to come through, and it releases the air so it can start accelerating. So I feel a force. Now this, at time 0, the average velocity is 0. The instantaneous velocity is 0. But by the time it gets to here, it's undergone a uniform increase in its velocity, so by the time it gets up here, it's its maximum velocity. Now the average velocity is just going to be, if it's uniformly increasing, is just going to be the velocity that was at the center part. in that pattern. Okay, so I get a delta x over delta t, and here the velocity is greater than average. Now the instantaneous velocity, if I simply take this and I say, well, now I have this is my new t2, and this is my new x2 coming here, and then I get closer and closer and closer, and let's say I blow this region up, I take this little interval, and I blow it up, so now I see something like this, and do that, get closer and closer and closer, so that my time interval between t2 and t1 goes to 0. Okay? We define that as a limit as delta t goes to 0. And really what we're saying is the slope of that line is more, the slope of the average velocity is more perfectly describing the instantaneous velocity, or the velocity over the velocity over a moment in which we describe that speed. So for example, that projectile is going through the pipe, but at some instant, I want to know what the velocity of that is. Calculus will give that to me because the time interval in which I measure that has gone to 0. Okay? So what we say is v then becomes dx dt, or that change in which the interval becomes extremely small. Okay? And so that's where we get this, what is referred to as the instantaneous velocity, and that's simply just the derivative of the positioning function with respect to time. Okay? Now it's a long-winded thing, but we will use quite a bit of calculus in this course, so I hope that it's intuitive as we discuss it. All right. So now, so this is the definition of velocity. What is the definition of acceleration? Well, what we're going to say is, we're going to say A average is just the change in velocity as a change in time. So we saw that curve that we drew up when we dropped the slide through there. As we dropped the slide, what you could see was that the average velocity was increasing as a function of time linearly. Okay, so if I take the average velocity and I look at that, I say, what was the velocity at the end point? And probably some of you can still see it, but if I look at the velocity at the end point versus the velocity at the initial point, and you can see there's this steep line here, that is v2 minus v1 over that time interval over which that occurred, that change, or the time that it took for that slide to fall through that laser beam. All right, so now if I go back to this curve, as you recall, if I look at that projectile motion, I get a quadratic behavior and then it goes linear. What would the velocity curve for this look like? So this is position as a function of time, right? What would velocity as a function of time look like? Yes? Okay, good. That's right. Okay, so if I take a quadratic, right? If I have y equals x squared, and I take the derivative with respect of y with respect to x, then I get a straight line for dy dx, right? Because I have x squared, so I just get the derivative is 2x. Okay? So what that becomes, if this is quadratic, which means it's just growing as, for example, y equals x squared, and then it goes to y equals x, then what I have is something that looks like this. Okay? Over the time interval that it's accelerating, it's increasing its velocity linearly as a function of time, and then when it stops accelerating, then the velocity is constant. Okay? So that's what's happening in these systems. Now, once again, A instantaneous is just going to be dv dt. Now, what would dv dt be in this particular case? So if I look at this interval of time in which there's undergoing uniform acceleration, yes?
It would be straight line on the increasing in energies here.
Okay, good. And A, in this particular case, would be the slope of this line, right? Because that is telling me how the velocity is changing as a function of time. And for constant acceleration, the velocity is uniformly increasing in time. So if we just go back to that projectile motion, or if I just go to dropping that slide, what that means is that the velocity is linearly increasing, which means at each passing moment it is proportional to the time that passes. Okay? So if I take dv dt, which is just the slope of this line, it's constant. And it's linear here, which means that the acceleration is just going to look like a positive number that's proportional to the slope, and then at this point there is no acceleration, and so the acceleration would be 0, which is basically just to state that there's no more force acting out on it after that projectile comes out, okay? And then it's just moving at a constant speed, and so there's nothing accelerating, causing it to go faster or slower. Okay, so if A is equal to dv dt, and we know that v is dx dt, then we see that the acceleration is the second derivative of the position with respect to time. Okay? So now we can go back to these curves of x as a function of t, and then I can find A by simply taking the second derivative with respect to time. I do a little dance or something? You guys look like you might be, I might be boring you to tears. Okay. So, is anyone a good break dancer? No? Or nobody wants to share it? If you're a good break dancer, let me know in private, and then we'll maybe have you do a couple moves and things start getting slow. Okay, so I'm not a good break dancer. Okay, so if I have this function x is equal to 4 minus 27t plus t cubed, what is the velocity, what is the instantaneous velocity of this particle? So this is, what this says is the position of a particle is governed by this equation, which is a function of time. Okay? And I'm going to assume here that the units here are meters. Okay? That this is position meters. I didn't write the units here, but it's important to realize that if this is 27, what we mean is that this is actually 27 meters per second. So that if I'm using seconds, the units. Okay? So if I have that, what is the velocity as a function of time? Sorry? Okay. So I get 3t squared minus 27. Okay? Right? So all that we did was take the derivative here, and I get Now, if I were to take this and just look at this for a moment as a function of time. Okay. What this does is something that looks something about like this. Okay. What does this mean physically? It means I have a particle. Okay, this is time axis and this is the position axis. I have a particle that's initially starts moving this way. And in about 3 seconds, it stops and starts moving the opposite direction. And then it starts to really move rapidly in the opposite direction. So it goes a little bit like this. Okay? That's essentially what this particle is describing on a 1D graph. But this is basically showing that it's undergoing negative displacement over these time intervals, and then turns around, stops. This actually, because dx dt is 0, which means that there's no velocity, and then it starts going rapidly increasing to the right. Okay, and so if I look at the acceleration, right, of dv dt, right, then this goes away, and what you see is that I just get a 6t. So the acceleration is actually uniformly increasing as a function of time. It's not constant as a function of time. Okay. So these are just some really basic calculus reminders, hopefully for everyone. Okay. Now let's go through the equations that we're going to be using for quite a while here in this course, quite a few lectures. I'll just write down the equations of importance. Okay. So what we're going to say is B, and if we don't write something like B final or B2 or anything like that, know that that represents the instantaneous velocity. Yes? So I'm going to actually talk about that at the end of the class. Okay, other questions? Okay, so V is equal to V0 plus AT, which means that if I look at the velocity at some particular time t, it's a function of how fast it was initially going plus the acceleration times time. Okay? So these are for importance, and I want to emphasize this is for constant acceleration. Such as, for example, dropping something under a gravitational field where it's close to the Earth and g is roughly constant. Okay, so v is equal to v0 plus at. X is equal to x0 plus v0t plus 1/2 a t squared. V squared is equal to v0 squared plus 2x minus x0. X is equal to x0 plus 1/2 v0 plus v times t. Okay. So now, because we have constant acceleration, A is equal to A average. Okay? Just it's constant, so we're going to assume that A is equal to A average. Well, A is equal to A average, and we get V minus V0 all over T. Okay? This literally means the time interval. And we're going to assume that time 1 is just going to be 0. Okay? So we're just considering the total time duration here when we write T here. And if I look at this, okay, I can simply just take this up. I see that if I bring the A up, if I bring this T, I have A times T is equal to V minus V0. And when I write this, this means, this implies, this statement, right? This is a mathematical statement. This implies, which means I can then rewrite this as V is equal to V0 plus AT. Okay, so all we did was took our average velocity, and we said that that is the delta V over delta T. But we said that the T0, we're just going to define to be 0. And so we just left with the final T. And this is the change in the velocity. And so with that, we can just rewrite this statement as V is equal to V0 plus AT. Okay? Now, if I look at this equation now, the average, that's just x minus x0 all over T. That's how we defined it earlier. We had a delta x over delta T. Now this is our delta x. And once again, I've said T1 is 0. Okay, so if I look at that, I use this, and I say the average is also equal to just the average velocity at the endpoint and the velocity times 0. And I use this. Okay, so now what I'm going to do is I'm going to combine these equations here. What I really want to do is I want to write something also in terms of an x as a function of time. Okay, so I know that x is equal to 1/2 v0 plus v plus 0. So I just took my, times 5. And now what I'm just going to do is I'm going to apply these. So I've written things up here. For example, I've written a v here, and I want to start incorporating this in this equation. So if I just say that this is equal to 1/2 v0 plus at plus v0 times t plus x0. So all I did is I took this definition that we used up here and substituted in this. And that's where this comes from. Well, now we have 2 v0 multiplied by half, so I just get a v0. And then I get an at, 1/2 at, and then I get this at times another t, so I get 1/2 at squared, and I'm left with x0 plus v0 times t plus 1/2 at squared. Okay? So all we did was use the definition of this average velocity, okay? Put it into the equation that we used to define average velocity in terms of x, and then substitute it in this, and that's where we get this from. Okay? Now this can also easily be done from calculus. Okay? If you have a uniform acceleration, okay, a is equal to dv dt, and you integrate to both sides, you'll get this equation. And then if you do this again and integrate, you'll end up with this equation. So calculus will do all this very nicely for you. Okay, so now what we want to do is we now want to do something that's independent of time. So one of the really amazing things about Napoleon was that he was very, very good at using artillery when he was doing his conquests. And so if you know how long a projectile's in the air, then you can say, oh yes, it's going to land over here. But why would you want to keep time in a lot of these situations? Why not just know how fast the shell leaves and the angle that you have, and then you can do very good predictions of how far it's going to go. You have what's called a range. And you can get things that are independent of time. We want to remove time as a variable. So suppose I have acceleration, I have initial and final positions, and I have this, those sorts of things. Then I can remove time from it. So if we want to get this equation right here, you'll notice, if you know the initial velocity squared and its displacement, then you can find the final velocity if you know the acceleration. Oh, I'm missing the acceleration here. Sorry about that. 2ax minus x. Yes. Okay. Sorry about that. That should actually have a in here. That's one of the bad things about being H. Make a mistake over, but we'll edit that out. So now what we're going to do is we're just going to simply use this v is equal to, if I look at v minus v0 and solve for time here, then I can just bring v over to v0 to this side, so I have v minus v0, and then I'm going to bring a down. So I have t is equal to v minus v0 over a. All right, so what we want to do is we want to get rid of time. So we have multiple equations, and so we're going to solve for time and then substitute time into another equation, and then we can solve for it. So now, if I look at this equation right here, I have x is equal to x0 plus v0t plus 1/2 at squared. If I say x minus x0, this is just simply the displacement, the total displacement that we've undergone. Okay? And then I get this is v0, and I have a v0 times t. Well, now I substitute the t that I got up here. So I have a v minus v0 all over a. And then I use one more here, 1/2 a v squared minus 2v0v plus v0 squared all over a squared. So all I did is I took this t, I substituted into here, but since I have an at squared, I needed to square what was on the, I needed to square what was in here. So I get a v squared minus 2v0v plus v0 squared. Okay. So there's a lot of math here, but I just want to show you some things here. So v0v, so I get a v0v here minus a v0 squared, and this is all over a, and this is all over a, plus 1/2. One of these a's cancels with this a, and then you can see I get a v squared minus 2v0v plus v0 squared all over a. This cancels with that, okay? And then we are left with a v squared, and we're left with a v0 squared. But this, there's a 1/2 v0 squared over a, and then there's a minus v squared, v0 squared over a. Okay? So if I look at this, this gives me a v squared all over 2a from here, and then I'm going to get a minus v0 squared all over 2a is equal to x minus x0. 2a. 2a, I have 2a in both the denominators here, so I can bring in 2a. So I can see that I get a b squared minus b0 squared is equal to a x minus x initial. Okay, so lovely equation. So how many of you saw the video carefully after I showed it last time? One of the questions was if I dropped an apple that fell on Newton's head, was dropped from a height of 3 meters. How can we find the speed at which it was, collided with a Newton's head if it fell from a height of 3 meters? Yes.
Well, first you need Newton's side.
Okay, so I'm saying it's the relative height from where it fell to where it hit on his head. Yes.
We assume that the final where it provided with and has an unknown. We have the v initial when we know it, we assume it's 0. We have the acceleration with the gravity, and we apply this.
Okay, good. So let's do that. So object in free fall. What we're going to assume that A is equal to G, okay, and we're going to assume that that is equal to minus 9.8 meters per second squared, which means that this is going downward. The minus means downward. And everyone has a slightly different convention, but when we use this minus sign, it just means that this accelerating downward, we define downward to be negative. And we define up to be positive. So now, if I say how fast was apple falling when it hit Newton's head, starting from 3 meters above his head. Okay. So let's look at all of the variables that we have here. What is the final position? Sorry?
0.
Okay, you can define, okay, so this is a good point. So if I define, this is x0, x final. I can define this to be, right? I can define this to be minus 3 down, or I can define it to be 0. You can define your origin wherever you want it to be. It's easiest to make one of these two things 0. Okay? What we're going to assume is that going down is negative. Okay? So x0, we can define either to be 3 meters. Okay? We can say x0 is 3 meters, and x final is equal to 0. Or we can say that, for simplicity, I could say that x initial is 0, and the x final is minus 3. I wouldn't do something like saying that this was 17 and this was 14, right? Just to have more numbers to keep track of. So define your origin to make your life the simplest. Okay, so, and we do that in as much as we can in physics, to define the origin to make your problem the simplest mathematically. Okay, so we know that x initial is 3 meters, x final is 0. Velocity initial is what? 0. We're going to assume that this apple started from rest, right? That it, how whatever happened shook, it fell. It made lateral shaking or something, but it just fell and got too ripe or whatever. So the initial velocity is 0. The final velocity is unknown. And what is the acceleration? acceleration is equal to minus 9.8 meters per second squared. Okay? So what equation would I use in order to determine the final velocity? How fast it was going? Well, this is a very good candidate, right? Because I know that this is 0. I know that the displacement here, right, is minus 3 meters. And I notice that this is, I know what this is, I know what these are, and I know what this is, right? So I have V. What's another way that I could solve this? There are other ways, there's many ways to do this. Okay, you want to use calculus? Brave and hearty soul, that's good. So what you can do, a simple way of doing it, is just simply to find the amount of time that it took, right? And then once you know the amount of time that it takes, then you just say V is equal to AT, right? And then you have it. V final is equal to V initial plus AT, but we know that V0, so on and so forth. So that's one way of doing it. I recommend doing it this way because we don't need to worry about time explicitly here. And so I just did this calculation, and I get that this is minus 7.6. So I can just see V squared is equal to 2A minus 3 meters. This is 2 times minus 9.8 times minus 3. And so I see that V squared is equal to the square root of 2 times, so I just get 6. And basically, I'll just call it 60. Square root of 60 is 7.6. Now, you'll notice is that this is that's the magnitude of the velocity, right? Because it's actually going down. When you take the square root, you get, sorry. I have this V squared is equal to 60. And I mean V is equal to plus or minus square root of 16. And you'll notice that this is minus since we're going down, right? The minus just lets you know that its velocity is in the negative direction. And so it gives you minus 7.6 meters per second. It's pretty fast. Didn't want to get hit with that. All right, how would I find the amount of time that it took to do that? Yes? Okay, good. So in this particular case, if I know what the final velocity is, then I can just use V is equal to V0 plus 18. That's right, good. It's all good. All right, so now, as was discussed earlier, how the area is under the curve. So this is okay, graphical integration. What does that mean? Okay, so we've already said that A is equal to dV dt. Right? Now, let's treat this a little bit like an algebraic formula. Okay? Algebra, you're all familiar with bringing things up to numerators, multiplying both sides. But let's just treat this. This is a constant. Well, actually, we won't assume this is a constant. let's just simply look at bringing this up here. So I get that this is A dt is equal to dv. Okay, now most of you are familiar with this sort of thing. But now, if I decide to integrate this, this is maybe something a lot of you haven't seen before, maybe you have. If I just integrate both sides now, and I say my integration parameter on the left side is with respect to time. My integration on the right side is with respect to velocity. If I then say I want to integrate it from some time t0 to some time t1, and then I say that this is a dt, and then I'm going to integrate dv from some v0 to v1. dv. Well, on the right-hand side, that's pretty straightforward, right? If I just take the integral of dv, I just get that this is v1 minus v0. Okay? Now, what is this on the left-hand side? Okay. Well, if a is a constant, then I get at. But what if a is not a constant? What if a is a function of time? Remember how I drew that curve up a little bit before where it had x is equal to 4 minus 27t plus t cubed? That equation? In that particular instance, a was not a constant, right? A actually was actually 6t, right, if you remember that. So if I have 6t dt, right, then I integrate it, then I'll start to get the area under the curve. Okay? What this means then is if I integrate the acceleration with over time, that is literally the area under the curve. The area under the integration, the acceleration curve, is the change in the velocity. Okay, so if I have a situation like this, where I have some acceleration graph, okay, if I integrate the area under the curve, that tells me what the change in the velocity is. Okay. This is really there's quite an interesting example that they give in the book about crash test dummies. And actually, I think they actually used a real person in this. So what they did is they took a person and then they simulated what would happen to the person by moving their seat forward as if they had been hit by rear-ended by another car at 10.4 kilometers per hour. So they just accelerated the seat. They wanted to see how the head and the torso accelerated. And the head and the torso had a different acceleration pattern. And I thought it was interesting what the head pattern did in this. And this is only at 10.4 kilometers per second, but the acceleration, so let me just draw got up to 90 meters per second squared over a 50 millisecond time interval, and then it started to drop, and then in the next 10 milliseconds, it went down to 50 meters per second squared. So this, if I look at that, that gives me this area under the curve, tells me the change in the velocity of the head as a function, it tells me the change in the velocity. Okay? So that head, as it's undergoing acceleration, it just shows me if I take this area under the curve, what that happens to the velocity of the head as it's doing that. So in order to find, for example, during this time interval, how would I find the area under the curve? base times the height. So I know what the base is, it's 50 milliseconds. I know the height, equivalent to 90 meters per second squared. Okay, so now that's so if I look at 1/2 the base times the height, the base is 1/2 times 50 milliseconds times the height, which is 90 meters per second squared. Now, I want to adjust the units here. So I said this is 1/2 times 0.05 seconds times 90 meters per second squared. Now, checking units again, right? We see that this second in the numerator here cancels with one of these seconds in the denominator, and I'm left with 0.05 times 90. Now, I can just take half of 90, I have 45, and I have 45 divided by 20. 45 divided by 20. So the head is going 2.2 meters per second after 50 milliseconds. And so that's a pretty remarkable change. So I know our time is out, but I just want to say one last thing. This integration of the area of the acceleration basically changes velocity. If I were to do this for the integration of the velocity as a function of time, I would find a change in the position of that particular particle. Okay, great. I will see